Hello everyone, welcome in the video lecture of Communication Engineering. In today's lecture, we are going to discuss digital pulse modulation and line coding techniques. So let us start with the lecture. First of all, let us understand what is the meaning of pulse modulation. In previous video lectures, we have seen continuous carrier wave modulation. Now, what is pulse modulation and why it is required? If we select, we know that what is modulation. Modulation is, in modulation we used to vary any one parameter of a carrier signal according to our information. If that carrier signal is in the form of continuous waveform like this, high frequency sinusoidal waveform, then the modulation done with the help of this kind of continuous carrier is called as analog modulation, for which we have studied amplitude modulation, phase modulation and frequency modulation. If we will select a train of pulses as a carrier signal instead of a continuous carrier wave, if we will select a train of pulses as a carrier signal and will vary any one parameter of these pulses, its amplitude, its position or its width according to the instantaneous value of our massive signal, then it is called as pulse modulation. So what is pulse modulation? In pulse modulation, our carrier will be in the form of pulse signal and its parameter will vary according to the massive signal. So pulse modulation we can categorize further as analog pulse modulation and digital pulse modulation. In analog pulse modulation, we have pulse amplitude modulation, pulse position modulation and pulse width modulation. What is the meaning of this pulse amplitude, pulse position and pulse width modulation? Pulse amplitude modulation is if the amplitude of these pulses will vary according to the amplitude of our massive signal, then it will termed as pulse amplitude modulation. Its width and position will remain constant when we are performing pulse amplitude modulation. Okay, what is pulse position modulation? In this particular figure, we can observe that these pulses are occurring at regular time interval. Regular time interval means the gap between these pulses is constant. So in pulse position modulation, what will happen as the amplitude of our information is varying, the position of these pulses will also vary. That will termed as pulse position modulation. Okay. Pulse width modulation. What is pulse width modulation? Here, if the width of these pulses will start vary according to the variation in the amplitude of our information, then it will become pulse width modulation. So these three categories of pulse modulation comes under the category of analog pulse modulation, that is PAM, PPM and PWM. In today's lecture, we are going to focus on the digital pulse modulation technique, which is pulse code modulation, differential pulse code modulation and delta modulation and adaptive delta modulation. After this, we will also discuss about line coding techniques, how we can convert digital data into digital signal. So let us start first with the pulse code modulation. So till now what we have studied, that the meaning of modulation is that we will have a carrier signal and any one parameter of the carrier signal will vary according to the massive signal. But pulse code modulation is little bit different from the usual modulation technique. What is pulse code modulation? In pulse code modulation, we used to convert analog signal into digital signal. So basically here we are modifying our information which is analog in nature into digital data or the digital signal. So this modulation of analog signal into digital signal we are calling as pulse code modulation. For the very first time, this PCM, pulse code modulation, was used for digitizing the voice signals. So for the first time, voice signals or the speech signals were digitized. Digitized means the analog signal will be converted. Voice signal is an analog signal and it was converted into digital signal with the help of a technique which is called as pulse code modulation. Okay. So pulse code modulation, in pulse code modulation we will not have any carrier signal, and the property of that carrier signal will not vary according to the message signal. Rather, here we will have 3 steps where we will convert our analog signal into digital signal. What are the 3 steps to convert analog signal into digital signal? The first step is to perform sampling, then the quantization, and then encoding. Okay, what is sampling? In sampling, we know that our analog signal or the continuous signal looks something like this. This is continuous in nature, continuous in time axis, continuous in time axis, and continuous in magnitude axis. What is the meaning of the word continuous? Continuous means for each and every time interval there will be some signal is available. Each and every time interval means if I will select 2 time durations, then there will be infinite time duration between these 2 time durations. Okay, so we can say we have infinite time intervals, and for each and every time interval some value of the signal is available. It continues in time also, and it continues in amplitude also. So in the first step of analog to digital conversion, that is sampling, we used to discretize this continuous signal in time axis. So what is sampling? Sampling is the process of converting an analog signal into discrete signal by discretizing this analog signal or the continuous signal in time axis. So in pulse code modulation, the first step is to perform sampling. The sampling we can perform with the help of pulse signals. So this sampled signal, sometimes also called as pulse amplitude modulated signal. So what we have done here, the amplitude of the pulses will vary according to the amplitude of our message signal, but the pulses are available at the discrete time interval. There is no signal between these 2 samples. Now our signal has been discretized in the time axis, or we can say the continuous signal has been sampled. Okay. The second step is to convert this time discretized signal into amplitude discretized signal. We are having 2 parameters in our continuous signal, continuous time and continuous amplitude. So the continuous time is discretized with the help of a process called sampling. The continuous amplitude will be discretized with the help of a process called quantization. What we used to do in quantization, we used to assign some levels with uniform or non-uniform gap from minimum to maximum voltage level of our continuous signal. What is quantization? In quantization, we used to discretize a continuous signal in amplitude axis. How we will discretize in our continuous signal in time magnitude axis? By assigning or by discretizing the complete amplitude in some fixed number of levels. Okay. Then we will assign binary to each level. It will use only 2 digits, 0 and 1. Then we have to divide this entire amplitude range only in 2 levels. The signal falling, let's say I have divided this complete range of the of our information in these 2 levels. The signal falling below this line will be encoded as binary 0, and the signal falling above this level will be encoded as binary 1. So if I want to transmit this particular sample, or this particular sample, I'll transmit binary 1 instead of this amplitude value. Or if I want to transmit this particular sample, or this one, or any one lying below this level, I will send binary 0 instead of that amplitude value. So this is quantization. In quantization we discretize amplitude axis, and then we will assign binary to each level. More will be the number of levels, more number of bits we are required to assign. So it will depend how many bits we are assigning or how many bits we have. So according to that we will assign level to our continuous signal. So in sampling, we are discretizing our continuous signal in time axis, and in quantization, we are discretizing our continuous signal in magnitude axis. After that, we will assign binary, and then we will say our analog signal has been converted into a digital signal. So this entire process of converting analog signal into digital signal is called as pulse quad modulation process for voice signals, for digitizing voice signals. Okay. Let us understand this quantization process in detail. What criteria we used to prefer when performing sampling of our continuous time signal, that is Nyquist criteria, according to which the sampling frequency must be greater than twice of FM. What is FM? FM is the maximum frequency component present in our masses signal. What is the meaning of this expression? That means these sample, at which frequency these sample will occur, it will be decided by a criteria which is called as Nyquist criteria. If we will follow this Nyquist criteria, then it will be possible to recover our information back from these sampled signal. Otherwise, we will not be able to recover our information back from this sampled signal. So if we want to retrieve our information, we have to use this Nyquist criteria, according to which the sampling frequency must be greater than equals to twice of maximum frequency component present in our masses signal. So this is about the sampling. Now what is quantization? How we can perform this quantization? Let us understand in detail how we can perform the quantization. So first, here we have this blue line is indicating our analog or continuous signal. First, we have discretized this continuous signal in time axis with the help of sampling. So let's consider that these are the value of the sample at these time interval T1 to T7. Now the signal is present after discretizing this analog signal in time axis at T1, at T2, at T3, 4, 5, 6 and T7 time instant. There will be no signal available between T1 and T2. Till this point, we have sampled or we have discretized the continuous signal in time axis. Now we want to perform the quantization. Quantization means now we want to discretize this continuous signal in amplitude axis also. Let us consider that the minimum amplitude of this continuous signal is 0 volt and the maximum signal value of this 0 to 5 volt. We can divide this range 0 to 5 volt into equal number of levels. That means, let us say 0 volt, 0.5 volt, 1, 1.5, 2, 2.5, 3, 3.5, and we can assign 0.5 levels to each voltage range in this manner till 5 volt. Okay. So each level is having equal amount of gap. This is called uniform quantization. If the gap between the two levels is uniform or similar throughout the quantization process, it is called uniform quantization. The gap between these two levels is called as step size. So I will use the word step size now onwards. So step size is uniform here. Step size means the levels, the gap we have provided is uniform, will have the similar amount of value or the voltage level. Now after dividing each amplitude level in some amount of voltage and in some amount of level, we will assign binary. We will start from, let us say 0 0 0 0 0 1 0 1 0 1 0 0 1 0 1 1 1 0 and so on. Now we will look at this sample. This sample is lying at this particular level. The binary assigned to this level is 101. So instead of sending this particular analog signal, what I will transmit 101. When we will look at the another sample, it is lying at this particular level. The binary assigned to this particular level is 110. So instead of sending this particular analog signal, what I will send 110. What 110 will indicate that the voltage level is 3 volt. It can be any other value also, but here in our example it is 3 volt. So in the next, the sample is lying at this particular value, which is 5 volt. Let's say highest amount of binary is assigned to this level is 111. So if I transmit 111, what it will indicate that a 5 volt signal is transmitted. So in this way, each sample will be assigned with a binary, or we will say that each sample is encoded, or what we will say that our analog signal has been converted into the digital signal. So this is the way we can convert our analog signal into digital signal with the help of sampling by discretizing in time axis, and with the help of quantization by discretizing in magnitude axis, and then by encoding the quantized data, we will get the digital data. Okay. So here we have obtained some relationship between the step size and the number of levels. If we know in how many bits we want to encode our data, or in how many bits we want to encode our information, it will decide the number of levels. For example, if I have only 1 bit for each level, then there is a simple relationship between the number of levels and the number of bits. If number of bit is 1, then the number of levels will be equals to 2. If number of levels will be equals to 2, that means the entire 0 to 5 volt range will be divided only in 2 levels, 0 volt, then 2.5 volt, and then 5 volt. Then entire samples which is lying between 0 to 2.5 volt will be assigned with binary 0, and the entire samples which is lying between 2.5 to 5 volt will be assigned with binary 1. So this is easy, but it will create very high amount of noise in our transmitted signal. Why? Because I will see this particular sample is lying here and having magnitude, let's say 1.5 volt. This particular sample is lying here, which is having amplitude level, voltage level is 1 volt, and this particular sample is 2.5 volt. So a voltage, a signal which is having a voltage level of 1.5, 1 and 2.5 volt will be assigned with binary 0. So binary 0, what it will indicate? A voltage level of 2.5 volt. So it will assign only 2 bits, or it will divide the entire amplitude range only in 2 levels, then it will add very high amount of noise in our transmitted signal. So what we have to do to improve the efficiency, or to improve the transmission efficiency, we have to increase the number of levels, so that each sample will fall into its nearest voltage level. So it will increase the number of levels, the number of bits will also increase. That means if the number of levels are more, then the binary assigned to each level will also increase with the help of this particular relationship. Now this increment in number of bit will create one more problem, that is the requirement of bandwidth. It will increase the number of bits, it will increase the bandwidth requirement in PCM. Now let us understand what is the bandwidth requirement of PCM signal. When we want to transmit our signal with the help of this PCM process, that means when we want to digitize our signal with the help of pulse code modulation process, we require some amount of bandwidth to transmit that particular data. What is the bandwidth requirement? The bandwidth requirement of PCM signal depends upon the bit rate, that is RB. What is bit rate? Bit rate is the number of bits transmitting per second. The bit rate for PCM can be given as n into fs, where n is the number of bits and fs is the sampling frequency, which is fs is twice of fm. Okay. So bandwidth requirement in case of PCM is half of the bit rate. Minimum this much of bandwidth we require in case of PCM. Though the bandwidth will depend upon the number of bits, but even if we are using minimum number of bits, we require minimum bandwidth as half of the bit rate. So if we will put the value of bit rate in this formula, we will get the minimum bandwidth requirement for PCM as n into Fs by 2. So the bandwidth is directly proportional to the number of bits. It will increase the number of bits to improve the efficiency, transmission efficiency, and to reduce the quantization noise. The bandwidth requirement for PCM will also increase. So there is a trade-off between the number of bits or the quantization noise and the bandwidth requirement in case of PCM process. So what we can do to reduce the bandwidth requirement, we have another method which is known as differential pulse code modulation. What is differential pulse code modulation? First of all, why this DPCM is required? This DPCM is required to save the bandwidth. In case of PCM, each sample will be encoded, original sample will be encoded and then transmitted. In case of differential pulse code modulation, we used to take the difference of two samples and then that difference will be quantized and then encoded and then transmitted. So it will help us to save the bandwidth requirement. So here, what is differential pulse code modulation? In case of differential pulse code modulation, we know that in case of voice signal or speech signal, the correlation between the two samples is quite high. Correlation means similarity. If the similarity between the two samples is high, then it is not required to repeat the transmission of each sample. What we can do, we can take the difference of two adjacent samples and then quantize them and then encode them and then we can transmit. It will help us to reduce the bandwidth requirement. How it will help us to reduce the bandwidth requirement? Let us understand with the help of this particular graph. Here in this graph, we can observe that the samples are present at TS, twice of TS, thrice, 4, 5, 6, 7, 8, 9 and 10th instant. Corresponding to each sample, we have some binary starting with 000, 001, 010, 011, 100, 101, 110 and 111. So in this particular figure, we can observe that the sample 4, 5 and 6, 3 of them are carrying the same information. If we are using the PCM process, then in PCM process we will transmit 3 of them individually. So we have to transmit 110, 110 and 110. But in differential pulse code modulation, if we are using differential pulse code modulation, what we will do, we will consider the difference of these two samples and then quantize them and then transmit them. So the difference of these two will become 0, again the difference of these two will become 0. So we have no need to transmit these 3 signals repeatedly. Okay, what these type of information is called, where the samples are carrying the same information, this is called redundant bits. This is called redundant bits. What is redundant bits? Redundant bits here, redundant information means where the samples are carrying the adjacent samples are carrying the same information. So in DPCM, what we can do, by taking the difference of adjacent samples, we can reduce this redundant information and finally we will be able to save the transmission bandwidth. Let us understand this process with the help of one more graph. Here we have our original analog information that we want to digitize and transmit. Here we have the digitized PCM signal. What we have done here, we have sampled this analog information by discretizing the time axis and then by discretizing the magnitude axis, we have quantized this information, analog information, and we have assigned binary to each level. Here we have total 8 number of levels starting with this 0 time axis. So we have used with the help of this particular relationship, if n is 3, then the number of levels will become 8. If n is 3, then the number of levels will be 8. Okay. So 000, 001, 010, 011 and so on. Now if I want to transmit this particular sample, it is close to this level, I will transmit it with the help of 101. Next I want to transmit this particular sample, it is close to this level, it will be transmitted with the help of 100. One more thing, let us consider one more sample here, which is lying in between these two levels. In this case, if a sample is lying in between the two levels, we will check whether it is nearest to the upper level or whether it is nearest to the lower level. To whichever level it is near, we will assign that particular binary to that particular sample. Okay. So now if we are digitizing this analog signal with the help of PCM, we will transmit each original sample with the help of these bits, with the help of which we have encoded the signal. But in case of DPCM, differential pulse code modulation, what we will do, we will consider the difference of two adjacent samples. Let us consider that this is of 2 volt and this is of 1 volt. This is of 0.5 volt and this one is of 0.8 volt. So the difference of these two, 2 and 1 volt, will become 1 volt. So rather transmitting the binary corresponding to 2 volt sample and 1 volt sample, what we will do, we will take the difference of these two, then assign the levels and then quantize that 1 volt sample signal and then transmit it. Okay. So the difference, if we will consider the maximum voltage range in this PCM is 0 to 2 volt, if the maximum voltage range in this PCM is from 0 to 2 volt, it will reduce from 0 to 1 volt in case of DPCM. This is just an example. If the maximum voltage range in case of DPCM is varying from 0 to 2 volt, so after taking the difference, it has been reduced from 0 to 1 volt. So if the amplitude range will be decreased or will be reduced, then we require less number of levels. If we require less number of levels, then automatically the bit requirement will reduce. If the bit requirement will reduce, then the bandwidth requirement will also become less as per this relationship. So in case of DPCM, what we used to do, we used to take the difference of two adjacent samples, then we will quantize that difference and then used to transmit the coded data corresponding to that particular quantized signal. That will help us to save the transmission bandwidth. Here we have reduced the bandwidth requirement, but still we have not reduced the bandwidth requirement to as minimum as possible. So there is one more variant in the similar scenario, that is known as delta modulation. Delta modulation is also called as 1 bit DPCM or 1 bit quantizer, or it is also called as 1 bit pulse code modulation. Why it is called as 1 bit pulse code modulation? Here, whether the amplitude range is varying from 0 to 2 volt, 0 to 5 volt or 0 to 10 volt, we will assign only one, or we will transmit only one binary at a time. That means there will be no combination of bits like in the previous case 00 or 000, depending upon the number of bits we are using. Here we will transmit only one bit at a time. The value of n in case of delta modulation is only 1 bit at a time. How we can transmit our analog signal by encoding only with the help of 1 bit? Let us understand. So let us first discuss what is delta modulation and how we can assign only 1 bit to each sample. In case of delta modulation, first we have to perform the oversampling. This kind of modulation we can do only with those signals which are highly correlated. If they are not, first we have to do the oversampling. Oversampling means we have to select the sampling frequency much greater than twice of FM. So what it will do, it will increase the sampling frequency, the samples will come very close to each other. That means they become highly correlated. Okay. So this delta modulation cannot be performed with all kind of signals. It can be performed only with those signals where the correlation between the signal is very high, or we have to perform the oversampling. Then what we will do next, we will compare the adjacent samples. If their difference come out to be positive, we will assign binary 1 to that particular sample, and if that difference will come out negative, we will assign binary 0 to that particular sample. So how we used to assign binary in case of delta modulation? In case of delta modulation, let us consider that this is our information, analog information. Now with the help of oversampling, first we will sample this analog information in time axis. Okay, so here what we can observe, that this is our sample 1, this is our sample 2, and this is our sample 3, and so on. But these samples are very close to each other. Why they are very close to each other? Because they are highly correlated. Correlation means similarity. So the first step to perform the delta modulation, we require high amount of correlation. If it is not available, then we can achieve with the help of oversampling. Okay. So now what we will do in delta modulation, we will not discretize these samples in magnitude axis. Rather what we will do, we will compare these two samples. If their difference will come positive, we will assign binary 0. If their difference will come negative, we will assign binary, if their difference will come positive, we will assign binary 1. If their difference will come negative, we will assign binary 0. So if we will look sample 1 and 2 and compare them, sample 2 will be compared with sample 1. Sample 2 is greater than sample 1. So what we will assign? We will assign binary 1 corresponding to the first one. Now we will compare sample 3 with sample 2. What it will be? Sample 3 magnitude is greater than sample 2 magnitude. We will again assign binary 1. In the similar manner, we will keep on assigning binaries. Now here, when the signal will start decreasing, this sample has lesser magnitude than this sample has lesser value than this sample. So their difference will come negative. So what we will assign now? Binary 0. Similarly, when we will compare this sample to its previous value, it is lesser in magnitude in compared to this sample. We will assign again binary 0. So in this manner, what we will do, we will not discretize this analog signal in magnitude axis. Rather we will compare two adjacent samples, and if their difference will come out positive, we will send binary 1, and if their difference will come out negative, we will transmit binary 0 corresponding to that. So the binary or the bit is fixed, either 1 or 0. That is why it is called as 1 bit quantizer or 1 bit DPCM. Okay. So here we have the modulator diagram for delta, block diagram of delta modulator. In this diagram, the first is oversampled original signal. Its difference will be taken with its delayed version. That means the next sample will be compared with the previous one. Their difference, if this value will come out positive, here we have 1-bit quantizer. What is this 1-bit quantizer? It will generate either binary 1 or 0. Binary 1 will be generated if this difference is positive, binary 0 will be generated if this difference is negative. Then again, with the help of feedback, the next sample will be predicted and then it will be compared with its previous value. So what we can say here, the present input of the delay unit, the present input of this delay unit is equal to the previous output of the delay unit plus the present quantizer output. Whatever we are having or whatever quantized output we are having, and then it will be added with its own delayed output. Okay, so in this way we can convert analog signal into digital signal with minimum bandwidth requirement. This is the advantage of delta modulation over DPCM or PCM, that it is 1-bit quantizer. Here we don't have to follow this bandwidth requirement formula, that is NFS upon 2. Here bandwidth is fixed, we are transmitting either 0-bit or 1-bit. So here it is having minimum bandwidth. It is very easy to design, its modulation and demodulation is also very easier. But if we are performing delta modulation, then it may suffer from two kind of errors, or it has two limitations, which is called as slope overload distortion and granular noise. What is slope overload distortion? This used to come when we used to consider the gap or the step size very small. The granular noise used to occur when we used to take step size large. What is the meaning of this step size small or large? Here we are comparing each sample with its previous value. So this increment in the sample value, this difference, which is called as step size. This step size we used to fix in the starting. If we take this step size too small, then slope overload distortion may occur. If we used to consider this step size too large, then this granular noise may occur. Now what is this slope overload and granular noise? In case of slope overload distortion, when this kind of noise will occur, if our information, original information, analog signals amplitude is varying very rapidly, and we have considered the step size in the starting too small, then it may not be able to follow the rapid change in the amplitude of our analog information. What is slope overload distortion? If we have fixed the step size too low and our information is varying too rapidly, then this staircase approximation may not be able to strictly follow the rapid changes in the information, and we may get wrong bit or the wrongly encoded output. It should be because the information is changing very rapidly, so the next sample will obviously greater than the previous one, but we will keep on getting 0 because it is not able to follow the variation in the signal. It is called slope overload distortion. The second is granular noise. It occurs if we consider the step size value too large. So if we have considered the step size value too large and our information has become constant. Constant means that there is no changes in our information. But if the step size is too large, then it will keep on crossing the constant information line and will keep on getting alternative bits in our output. It should be constant, but because it is constantly changing, we will get change in our output data. So this is called granular noise. It occurs when the step size is too large. Slope overload distortion occurs when the step size is too small. So these are the two limitations in case of delta modulation that occurs due to because we have fixed the step size in the starting. So what we can do to eliminate or to reduce, we cannot eliminate these two noises, but we can reduce these two problems of delta modulation. With the help of technique that can reduce these two types of noise is called adaptive delta modulation. What is adaptive delta modulation? In case of, as the name indicate, adaptive delta modulation. Adaptive, what is adaptive? Step size is adaptive. In the previous case, delta modulation, step size is fixed, either small or too large to follow the variation or to follow the constant information. Here we make the step size variable. Step size now will vary according to the variation in the information. If our information is varying quickly, the step size will become double or thrice of its previous value, and if our information is becoming constant, then this step size will become half of its previous value. So, in case of adaptive delta modulation, what is adaptive delta modulation? It is a technique with the help of which we can minimize the errors of delta modulation by making the step size adaptive to the variations in the input signal. How we can make step size adaptive to the variation in the amplitude of the masses signal? We have to apply a kind of logic control, step size logic control. The remaining block diagram will remain same. Here we have the original oversampled signal. Its difference will be considered from its delayed unit, and if its difference is positive, then the output is 1, and its difference is negative, then the output is binary 0. But the step size now will vary. How the step size will vary? In this figure we can observe that the amplitude of our information is varying very quickly at this point, and at this point the information is getting constant. So, what is one way to apply this step size logic control? That if the step size means this difference. So, if the step size increases or decreases according to a specific rule. What is that rule? For example, in this 1-bit quantizer, if the output is high or if the amplitude is changing very rapidly, then the step size may be doubled, as we can observe in this case. Here the delta 2 is greater than delta 1. This is the step size for this particular voltage level, and here this is the step size for this particular level. So, in adaptive delta modulation, if the information is changing rapidly, if we will get two continuous one, for example, the next step size will become double of the previous step size. Then it will be able to follow the changes in our information. Now, here we can observe our information is becoming constant. So, if we will get two continuous 0, the step size for the next sample will become half of the previous step size. So, in this way the step size will be adaptive to the variations in the amplitude of our information. It is it will be able to follow the variation in our information. So, in this way this adaptive delta modulation will help us to reduce the errors that may occur in case of delta modulations. Okay. Last we have line coding techniques. In line coding techniques, let us have one example. In line coding techniques, what is line coding technique? Line coding technique is a process with the help of which we can convert digital data into digital signal. In the last three techniques, what we have seen that our analog information is converting in digital data. Digital data means representation of the analog signal in terms of ones and zeros. This is called digital data. But this is just a representation. We cannot transmit this representation. We require some kind of signal to transmit this particular information. So, what is line coding technique? Line coding technique converts a sequence of bit which is digital data into some kind of signal which is called as digital signal. Okay. So line coding technique is a technique to convert digital data into digital signal. We can assign a fixed amount of voltage level to each binary in a particular manner. We have three basic line coding methods: unipolar, polar and bipolar. So we are going to take an example how we can represent our data into signal with the help of these three techniques. The first one is unipolar NRZ. NRZ means not written to 0. Unipolar means single polarity, uni plus polar. Single polarity means if this is the time axis, let's say it is 0 volt, above it will have positive polarity and below we will have negative polarity. So in unipolar NRZ, we will assign a positive polarity of fixed voltage level corresponding to binary 1 and no signal corresponding to binary 0. So in this way, we can represent our data into signal with the help of unipolar NRZ. The second is RZ, return to 0. What we will do in case of return to 0? Unipolar return to 0. I am taking the example of unipolar return to 0. In return to 0, for half of the bit interval, the signal will remain high, and then for next half interval, it will return to the 0 level. Okay, again no signal for 0. Wherever there is signal or polarity, for half of the duration it will remain high, for another half duration it will return to the 0. So in this way we can represent our return to Z line coding, return to Z digital signal of the digital data. Second is polar NRZ. In case of polar NRZ, we will assign positive as well as negative polarity to our bits. Positive polarity corresponding to binary 1 and negative polarity corresponding to binary 0. So wherever binary 1 will occur, we will assign positive polarity, and wherever binary 0 will occur, we will assign binary negative polarity. Then next, bipolar encoding, and this bipolar encoding is also called as AMI, alternate mark inversion. In case of bipolar encoding, again we will assign both kind of polarity, positive as well as negative, but the both type of polarities will be assigned to a single bit. We will assign positive polarity to one bit and negative polarity to one bit as well. So for the first one, if we are assigning one positive polarity, for the next one it will be negative, then for the next one it will be positive, negative and so on. So in this way we will assign alternate polarity to the alternate ones and no signal corresponding to binary 0. The last is Manchester encoding. In case of Manchester encoding, we use positive and negative polarity to each bit. In case of 1, for the first half it is positive, for the next half it is negative. For binary 0, the first half is assigned with negative and the second half is assigned with positive polarity. So if we'll assign our digital data in this particular manner, it is called as Manchester encoding. The selection of these line coding techniques depends upon some properties, that is self-synchronization, capability of error detection and correction, the power spectral density, the DC power content should be 0, it should be bandwidth and power efficient, and it should have transparency. That means it should be capable of detecting long series of ones and zeros. So depending upon these properties of the line coding, we can select any one of them. So this is all about this lecture. If anyone has any query, you may ask with the help of chat box. Okay.